In No Preferred Reference Frame at the Foundation of Quantum Mechanics, physicist W.M. Stuckey, that's me, mathematician Timothy McDevitt, and philosopher Michael Silverstein show that the principle of information invariance and continuity at the basis of information theoretic reconstructions of quantum mechanics reveals the relativity principle at the foundation of quantum mechanics, exactly as it exists at the foundation of special relativity. The principle of information invariance and continuity simply states the total information of one bit is invariant under a continuous change between different complete sets of mutually complementary measurements. Bruckner and Zeilinger's principle originated with what is widely regarded as the first axiomatic reconstruction of quantum mechanics based on information theoretic principles by Lucian Hardy in 2001, Quantum Theory from 5 Reasonable Axioms. There, Hardy noted that by adding the single word continuous to his fifth axiom concerning reversible transformations between pure states, classical probability theory became quantum probability theory. If we apply that to the b-hat Stern-Gerlach measurement of a spin 1/2 source with spin up in the z-hat direction, and draw our qubit probability space, or Bloch sphere in real space, with our complete set of complementary spin measurements, jx, jy, and jz, along x hat, y hat, and z hat respectively, we see that the SU2 invariance of qubit eigenvalues between different spin measurement operators in Hilbert space per information invariance and continuity entails the SO3 invariance of spin measurement outcomes between different inertial reference frames associated with complete sets of mutually complementary spin measurements in real space. As Weinberg points out, the Stern-Gerlach measurement of spin constitutes the measurement of Planck's constant h. Putting this all together, we see that the principle of information invariance and continuity entails the invariant measurement of Planck's constant h between inertial reference frames related by SO3. That is a subgroup of both the Lorentz and Galilean transformations between inertial reference frames. The classical constructor model of spin measurements predicts various deflections of the magnetic dipoles in the inhomogeneous Stern-Gerlach magnetic field. Thus, according to the classical constructor model, we would expect to measure S dot b hat equal cosine theta, but we can't measure anything other than plus or minus 1 due to MPRF. As a consequence, we can only recover cosine theta on average. That is, MPRF dictates that. So, solving that simultaneously with our normalization condition, we obtain the probabilities for +1 and -1 outcomes in accord with our qubit Hilbert space structure. The difference is that we are now using the invariant measurement of h per the relativity principle to obtain our expectation value, whence the probabilities for the outcomes, rather than the converse as done normally in quantum mechanics. Thus, the relativity principle, aka no preferred reference frame, requires the invariant measurement of Planck's constant h, and this underwrites the qubit Hilbert space, or kinematics, of quantum mechanics. As Stern and Gerlach rotated their magnets, they saw no change in the deflection pattern of atoms. This is in total analogy to MPRF requiring the invariant measurement of the speed of light c, which underwrites the Minkowski space structure, or kinematics, of special relativity. As Michelson and Morley rotated their interferometer, they saw no change in the interference pattern. In conclusion, the axiomatic reconstructions of quantum mechanics, based on information theoretic principles, reveal the relativity principle at the foundation of quantum mechanics, precisely as it exists at the foundation of special relativity, that is, demanding the invariant measurement of a fundamental constant of nature.